Hello learners, greetings of the day. Welcome to you to this lecture on alternating current of 12th standard physics. I am Balgopal Mahapatra, lecturer in physics of both Panchayat College, both. In your previous lectures, we have gone through different aspects in connection with alternating current, like what is self inductance, what is mutual inductance, what is LCR circuit, LCR oscillations, etc. And today we will take off what is transformer, what is a AC generator, and some numerical examples in connection with this. To begin with, what is a transformer? A transformer, it is nothing but a device which converts lower alternating voltage at higher current to higher alternating voltage at lower current. Or we may say it is a device which is used for changing the voltages of an AC power source to a higher or a lower value. So question arises, why there is a necessity of transformer? Why transformer is required? What happens in our day-to-day life? Different electrical instruments require different voltages for their operation, for their working. As for example, in an X-ray machine, an X-ray tube requires very high voltage, thousands of volts, but in some other devices like filaments of a diode, it requires as low as 6 volts for its operation. So some devices require very high voltage, very high potential difference, and some requires very small potential difference. And that possibility of getting higher voltage or lower voltage, it is viewable with the help of a transformer, which can either increases the voltage or it can decreases the voltage. And generally transformer here, it is based upon certain principle. How a transformer works? Transformer is based on the principle of mutual induction. Mutual induction means here what happens? An EMF is induced in a circuit due to a current changing in a neighboring circuit. So to say, it is the phenomenon of inducing EMF in the secondary coil due to change in current in the primary coil, and hence the change in magnetic flux in the secondary coil. So this is the principle basing upon which transformer works. And what is its construction? What are the different components of a transformer? Here you see, this is the schematic figure. This is the diagram of a transformer. It consists of two coils. One is named as primary P, the other is named as secondary C, and both the coils are wound over soft iron core. This structure, it is soft iron core, and here the number of turns and thickness of primary, so to say how many turns are there in primary or how many turns are there in secondary. So that depends upon the job to be performed by the transformer. Job to be performed means whether the output voltage is to be increased or the output voltage is to be decreased. That is the job of the transformer. So the number of turns and thickness of primary and secondary depends upon the job to be performed. And again here generally the core of the transformer, it is made up of soft iron. The core, it is made up of soft iron. We may say it makes use of soft iron core, and generally this soft iron core, it is in the form of laminations. Here you see in the figure how it is in the form of lamination, different layer, one layer, one lamination, second, third, fourth, fifth, sixth, and so on and so forth. So it is in the form of laminations which are properly insulated with a thin coating of insulation. One lamination is separated from the other lamination with the help of a insulation or non-conductor, you may say. in between two laminations, insulation must be there. So why insulation is taken, or why lamination is there here? Generally, it is in the form of laminations, or it is taken in the form of lamination so as to avoid formation of eddy currents, due to which certain energy loss may occur. So if it is taken in the form of lamination, we can generally check the formation of eddy current. And here input source of AC is connected across the three terminals of the primary. This is the AC source that provides input to the primary, but output is taken across the secondary across a load. It is a high resistance. Load is a high resistance across which output will be collected. So this is how the transformer is constructed, and generally how it works. What happens? How it acts? What is its action? When alternating current is connected in the primary here, then the current and hence magnetic field around the primary as well as around the secondary both will change continuously, because changing current in the primary will induce an EMF in the secondary, due to which a current flows. Both are very close to each other, so to say the current and hence magnetic field around the primary as well as the secondary will change continuously, and due to the phenomenon of electromagnetic induction here, the magnetic flux through the secondary results in the induction of EMF in it. This is how it works. Now, what is the theory basing upon which generally a transformer works? We may say, if the primary and the secondary coil are wound close to each other, one can assume for a fair approximation that the magnetic flux linked with each turn of the primary and the secondary should be same, right? And here let us say EP. What is EP here? EP is the EMF induced, EMF across primary. P stands for primary. So we may say here EP is the EMF induced in the primary due to flowing current through itself. So the EMF induced in the primary will be given by this expression minus NP d phi by dt as per Faraday's law. We know here NP is the number of turns of the primary, and similarly EMF induced in the secondary ES, it will be given by minus NS d phi by dt, NS being the number of turn of the secondary, NS be the number of turn of the secondary. Then here if we find the ratio, what is the ratio between ES by EP? Divide it. If you divide ES by EP, d phi by dt gets cancelled, negative sign gets cancelled, you will get NS by NP, and this is equal to always a constant K, which is called as transformer ratio. K is called as transformer ratio. So how to define this constant transformer ratio? Transformer ratio is defined as the ratio between number of turns of the primary to the number of turns of the secondary, or it is the ratio of EMF induced in the secondary to the EMF induced in the primary. As such, it will have no unit as well as no dimension. And here we may say, if a transformer, its efficiency is very good, it is an ideal transformer, at that juncture the power input should be equal to power output, or output power should be equal to input power. And you know, power, it is the product of voltage and current, EMF and current. So output power, it is the power ESIS, input power EPIP. So under ideal conditions for ideal transformer, these two will be equal, and from this we will get ES by EP equal to IP by IS. You mark, ES by EP will be equal to IP by IS. Earlier we have obtained ES by EP equal to K. So IP by IS will be also equal to K. So transformer ratio will be defined, can be defined either in terms of EMF or in terms of number of turns, or in terms of current through the primary and through the secondary. So this is the equation, ES by EP equal to IP by IS equal to NS by NP, that is equal to K. Now, to what extent a transformer works, how much efficient it is, out of the given input, how much is converted into output, that will be given by generally a quantity which is called efficiency. And here what happens, due to improper alignment, it is possible that the flux linked with the secondary may be a little less, but under ideal condition we are taking it as equal. Okay, so what is the efficiency of a transformer? Efficiency of a transformer, it is defined as the ratio between power output to the power input. ESIS is the power output, EPIP is the power input. And to find what is the percentage of efficiency, you just multiply this eta or ESIS division EPIP with 100. And for an ideal transformer, efficiency is taken as 100%. Okay, so we know transformer here, it performs two jobs. Either it can increase the voltage or it can decrease the voltage, and depending upon the performance or job to be performed, whether it will be to increase the voltage or to decrease the voltage, it depends upon the value of transformer ratio. So accordingly, two type of transformers are there. One is step up transformer, another is step down transformer. One is step up, the other is step down. So what is the difference between these two? A transformer in which voltage across the secondary is greater than voltage across the primary, it will be called as step up transformer. But if voltage across primary is greater than voltage across secondary, that I have already told to you, it will be called as, if voltage across the secondary means output is more than input, it is step up. But if output is less than input, it will be step down. That is to say, voltage across the secondary is less than the voltage across the primary, then it will be called a step down transformer. And for step up transformer ratio is greater than 1, means you know transformer ratio K is NS by NP. So NS is greater than NP. This will give you ES is greater than EP or IS is less than IP. So what is the condition under which transformer becomes step up? Number 1, your transformer ratio should be greater than 1. Number of turns across the secondary will be less than number of turns of the primary, and here current in the secondary is less than current in the primary. And just the reverse thing happens for a step down transformer. For this, transformer ratio is less than 1, number of turns of secondary is less than number of turns of the primary, and well, here you observe from this you can get ES is less than EP and IS is greater than IP. So that's the basic difference between your step up and step down transformer. And generally, although under ideal condition we may say that efficiency is 100%, while performing there are loss of energy in different forms. Okay, and here you see, in case of step up transformer, even if voltage is increased, current is decreased across the secondary. So a gain in voltage across secondary will result in a consequent loss in electric current through it, and vice versa. So now the energy losses in a transformer during its operation will be called as your losses of transformer, or losses in transformer, or energy losses in transformer, and various loss of energy occurs. These losses are iron loss, copper loss, hysteresis loss, flux leakage, and so on and so forth. So to begin with, what is the copper loss? Actually, this is nothing but the amount of energy lost due to production of heat when currents flows through the primary and through the secondary coil. You know, primary and secondary coil are made up of copper. When current will flow through it, as per heating effect of current, heat will be produced. So that heat produced due to the resistance of copper windings of the primary and secondary, when current flows through them, that is called copper loss. And this can be avoided by using thick wires for winding. We can avoid this if these wires are made thick, not thin. These will be made thick. Then second one, loss due to magnetic flux, flux loss, that is also called as flux leakage. What happens in actual transformer? The coupling between primary and secondary coil is not perfect, not properly aligned. So a certain amount of magnetic flux is wasted, it is leaked, and linking can be maximized, it can be made maximum by winding the coils over one another. Coils should be wound very close to each other. So that is what is called as flux leakage or flux loss. Third loss for a transformer loss is iron losses. Here, as a result of change in magnetic flux through the core over which the coils are wounded, currents known as eddy currents are set up. Okay, and these eddy currents are in closed circuits, and energy lost in the form of heat energy due to flow of these eddy currents are called as iron losses. So these iron losses, we may say these are eddy current loss, one type of loss, and the other will be hysteresis loss. The other will be hysteresis loss. And what is eddy current losses? Again, I am repeating. When a changing magnetic flux is linked with the iron core, eddy currents are set up so that it produces heat, and due to that energy is wasted. And these eddy currents are reduced by using laminated core. Already we have discussed in case of construction of transformer, generally core is taken in the form of laminations which are separated from each other by some insulating layer, or you may say insulations, right? So using laminated core instead of solid iron core, we can generally reduce it. Why? This is because in laminated core, the eddy currents are confined within the lamination. These are restricted within the lamination, and they do not get added up to produce larger current. Okay. In other words, we may say their paths are broken instead of a continuous one. Now, what is hysteresis loss? Here what happens in the transformer is that when alternating current is passed, the iron core is magnetized as per magnetic effect of current and demagnetized. So magnetization, demagnetization take place repeatedly over the cycles, and some energy is being lost in the process. Magnetization, demagnetization, one after another. Magnetization take place, demagnetization take place. What is the result? Some energy is lost in the process. Okay, and here generally what happens, this can be minimized by using suitable material with thin hysteresis loop. Actually here what is hysteresis? Actually hysteresis, it is the process by which your magnetic substance can be magnetized, and we may draw a hysteresis loop by drawing a curve showing variation of magnetic induction with magnetic field or intensity of magnetization with magnetic field strength H. Here the thing that I have discussed earlier, due to formation of eddy current, here you see what happens in a solid core and what happens in a laminated core. Insulations are there is no chance of adding of eddy current here. Okay, so these two are iron losses, one due to eddy current, another due to hysteresis losses. Another loss is there, losses due to vibration of core. In this case, some electrical energy is lost in the form of mechanical energy when the core vibrates due to flow of current, and hence a humming noise due to magnetostriction effect occurs. So due to that, some loss of energy is likely to be taken place. So these are the different losses. After going through these losses, now this is the case of transformer. Here this can be minimized. So minimization process already we have discussed, and transformer will find a number of uses in our day-to-day life. It may be generally, you might have known that transformer is generally used for long distance transmission of alternating current. It is generally used for long distance transmission of alternating current, and whenever there is a necessity of increasing or decreasing voltage, at that time transformer find its use. Transformer find its use, and at the power generating station and power consuming station, two type of transformer may be used, as you have already discussed. One is your step up, another is your step down transformer. Okay, so here what happens during long distance transmission for your current, generally the actual distance here between transmission point and the consumption center, it is very large. Okay, that is to say the distance between the stations where the power is generated and that where it is consumed is not small, it is very large, and the wire connecting the stations should have a large length, so they should have a large distance, due to which generally a potential drop occurs and loss of energy also occurs in the form of heat. Okay, so as these two losses are there here, this can be decreased. It decreases if transmission is done at low current and high potential. Amount of this loss can be minimized if transmission is done at low current and high potential, so that amount of energy transmitted is not affected. So for this, what is done, a step up transformer it is used. Okay, generally you know step up transformer converts low voltage and high current electrical energy at generating station into a high voltage and low current energy, and this high voltage electricity it is transmitted to the distant consuming station, and at the consuming station the voltage is stepped down in different steps, making use of step down transformer. So at the power consuming station one should use step down transformer, at the power generation station one should use step up transformer. Now what is a motor or what is a generator? We will discuss what is a motor or what is a generator. A motor or a generator is nothing but a device which converts mechanical energy into electrical energy. It converts mechanical energy into electrical energy. In the figure just we have shown the diagram here about your motor or generator, which is generally depends upon whether that electrical energy converted it is alternating character or steady. Accordingly two type of generator will be there or dynamos will be there, AC generator, DC generator, but we are concerned with AC generator. And generally why generator or motor becomes a necessity? Why is it required? Why there is a prompt for such an invention of motor? Generally in hydroelectric project we know mechanical energy is obtained by making water to fall from a greater height, and at the greater height the energy of the water there is completely potential. So that potential energy of water gets converted to kinetic energy as water falls down, and water is generally allowed to fall on a big toothed wheel in a hydroelectric project. Okay, and at the time kinetic energy of water makes the wheel to turn or rotate. Okay, it must generally fall tangentially so that that tooth wheel rotates, and the coil placed in between the two magnetic poles here, a coil is generally placed in between the two magnetic poles. It is coupled to the axle of the oil. It is coupled to the axle of the coil, and when the coil rotates, generally magnetic flux linked with it undergo a change, and hence EMF is produced, EMF is generated. So we say rotational kinetic energy. First, potential energy gets converted to kinetic energy to rotational kinetic energy, and now that rotational kinetic energy gets converted to electrical energy. That's why it is generating. It is a generator. It is generating electrical energy as EMF is induced in it. So we may say it is a dynamo or generator. And as already pointed out, it may be AC generator or it may be a DC generator. So what is a AC generator or AC dynamo or alternator? It is also called as alternator. It is nothing but a device which converts mechanical energy into alternating current, we may say. It converts mechanical energy into alternating current. And upon which principle it works? It works on the basis of the principle of electromagnetic induction. That is, when our magnetic flux linked with a circuit changes, an EMF is induced in it. Okay, and EMF is induced in it. That is generally the principle. And now let us discuss what are its construction. It consists of field magnets with polarity north pole and south pole, armature, slip rings, brushes, and loads. So what are its different components? You mark the figure. It consists of an armature here. It is PQRS. PQRS. Two positions are shown. Let us concentrate on the first position. PQRS is an armature. So this armature generally consists of large number of turns of thick copper wires which are generally wound over a soft iron core. Soft iron core is used to increase the magnetic flux linkages so that more EMF will be induced here. And the core is used generally, as I have already told to you, to increase the effective magnetic flux linked through the coil. Now, the armature can rotate in between the pole pieces of the magnet. This blue color, it is the south pole piece. It is the north polarity represented by the green color. N stands for north, S stands for south. So armature is capable of rotation in between the two pole pieces. And this north pole and south pole, these will be called as your field magnets, which provides uniform magnetic field. And if the dynamo is a small one, generator is a small one, permanent magnets can be used, while if it is a big one, permanent magnet cannot perform the job there. Generally, electromagnets are used as field magnets. Okay. Now, the other constituent is slip rings. These R1 and R2. R1, R2, these two are slip rings. And generally, the two free terminals from the armature, you see, this is one free terminal, this is another free terminal. It consists of a number of turns. This one free terminal is connected to ring R1, slip ring R1, and other free terminal of the armature, it is connected to slip ring R2. Okay. So, here the two free terminals from the armature are connected to the rings R1 and R2, and the rings are capable of rotation along with armature about an axis. This dotted line represents an axis. This dotted line here, you see, this is the dotted line. Armature can rotate about this. Rings can also rotate about the same axis as is done by your armature. Now, two wear brushes are there. What are wear brushes? One is B1, which is kept pressed with R1. B2, again this is kept pressed against R2, and these brushes are not welded. Actually, no welding is there between the slip rings and the brushes. Okay, these are not welded, hence they do not rotate along with them. Just pressed, slip ring will rotate, but brass will be in their position. They will not rotate at all. And last component of this generator is load. It is the instrument through which the generated alternating current. Which one? Your load, it is the instrument through which the alternating current that is produced here passes, and it is generally connected in between the two wire brushes B1 and B2. These brushes are in the form of wire, so we may say these are the two wire brushes. Now, how it works? How it works? When the armature rotates in between the two pole pieces of the magnet, how we are explaining here the working or operation or action. When the armature PQRS rotates in between the two pole pieces S and N here, then what happens? The magnetic flux linked with it changes between a minimum and a maximum value. When minimum, magnetic flux is BA cos theta. If cos theta is 0, magnetic flux is minimum. Means angle between area vector and magnetic induction vector is 90 degree. B and A is 90 degree. I am just changing here. Cos theta is 0 means phi is maximum, not minimum. Phi equal to BA. Okay. Theta equal to 0 means vector B and vector A are parallel. Area vector will be parallel. If area vector will be parallel to B, magnetic line of force, we may say surface area is perpendicular to magnetic line of force. Then flux linked with it is maximum. But when B and A are perpendicular, induction vector and your area vector, if these are perpendicular, area vector perpendicular means area and magnetic field are parallel, then theta is 90 degree. Then BA cos 90 0, so flux linked with it is minimum. And in between 0 and 90 degree, there is variation, 45 degree, 30 degree. So flux linked with the coil will change from minimum to maximum, right? And when again I am repeating here what happens here, when the plane of the coil is parallel to the lines of force, no magnetic lines of force cuts through it, so magnetic flux linked with it is minimum, as I had already pointed out. At that time theta is 90 degree, so phi B equal to cos BA cos 90, that is 0. But what happens when the plane of the coil is at right angle to the lines of force? Then magnetic flux linked with it is maximum. Plane of the coil is at right angle means area vector is parallel to magnetic field. So due to continuous rotation, this armature PQRS is rotating continuously, EMF is set up. How? You see, when it rotates continuously, what happens? PQ generally, as it rotates continuously, here PQ goes down and RS comes up. PQ goes down and RS comes up from the plane of the diagram, and induced EMF and hence currents are set up in the coil. And what is the direction of the current? That you can find applying Fleming's right hand rule. How can you find it? You can apply Fleming's right hand rule. You see, when it rotates, PQ goes down and RS comes up. This is the direction. PQ goes down, RS comes up. At that time, EMF is induced in it, and that due to that induced current flows in the direction PQ RS B1. You mark PQ RS B1 B2, again B1, sorry, it is flowing in the direction I am repeating, PQ RS B2 through the load, through B1, R1 and again P. This is the direction shown by this cursor taken by the induced current this way. Okay. This is due to the rotation during the first half. And in the second half rotation, what happens here? This PQ which has gone down, now it has come up. It has come up. And RS which had come up, now it goes down. Okay. And at that time, current flows in the direction shown S, R, Q, P. It is clear. B1, S, R, Q, P. B1 through the load, through B2, through R2, through R1 and again S. So direction of rotation about which your armature is rotating is shown by this arrow mark in both cases. It is rotating in anti-clockwise direction, and here you see in every case current flows in clockwise. Here this is in clockwise direction, this is also in clockwise direction. So these two figures, from these two figures we can very well conclude or infer that due to continuous rotation of the armature in between the two field magnet, EMF is induced, due to which current is flowing through it as in the direction shown in the figure. So here you see that if one way of current is taken as positive, then the reverse current is taken as negative, and that direction of current can be found by applying Fleming's right hand rule. So the current is said to be alternating and the corresponding wave is sinusoidal. It is said to be alternating and the corresponding wave will be sinusoidal. So we may say an alternating current is flowing through it. And now let us discuss what is the theory basing upon which it works. You see, this is the uniform magnetic field, B represented by parallel lines of force. This is the armature PQRS. It is rotating in this direction, and when it rotates, you know, as per principle of electromagnetic induction, magnetic flux linked with n turns of the coil is NBA cos theta. You see, this n cap gives the direction of area vector. It makes angle theta with the field direction. So it is NBA cos theta. And at time t, let its angular velocity is omega. And what is omega? Angular velocity and angular displacement theta. These are related by the relation theta equal to omega t. And in the beginning, at t equal to 0, loop is assumed to be perpendicular to the magnetic field. Means area vector is parallel to B. Surface area is perpendicular means area vector is parallel to B. So theta is 0. Okay. Now, in the beginning, but after t second, this is the position shown in the figure. So let us replace theta equal to omega t. So phi equal to NBA cos omega t. Let us differentiate phi with respect to time t. Thereby we will get d phi by dt equal to d by dt of NBA cos omega t. NBA being constant taken out, and differentiation of cos omega t will give you minus omega sin omega t. Differentiation of cos omega t with respect to time yields minus omega sin omega t. Thereby d phi by dt is nothing but minus NBA omega sin omega t. Now apply Faraday's law. This d phi by dt with a negative sign is nothing but EMF induced. So by comparison of this expression or substituting d phi by dt here, induced EMF in the armature or coil is NBA omega sin omega t. And you know, number of turns, uniform field V, area A, these are constant. If it rotates with uniform angular speed omega, NBA omega is a constant which may be taken as E0. Generally it is called as peak value of EMF. So E equal to E0 sin omega t, and you know this is an equation which represents a sine curve. variation of E with omega t will represent a sine curve which is sinusoidal in character or alternating in character. Here we have shown it in the figure. Here you see omega t is given pi by 2 pi, 3 pi by 2, 2 pi, 5 pi by 2, 3 pi, 7 pi by 2 and 4 pi along x-axis, and along y-axis we have drawn here what is called as your EMF. So this is the shape of the curve. It is alternating in character. Also here fraction of time period may be represented. So we may say here EMF is alternating in character. That means its magnitude changes continuously, but direction changes periodically. After equal interval of time, reversal of direction takes place. So this is the end of the chapter alternating current. Now in connection with this, let us work out some numerical examples, numerical problems. First one here, a 60 microfarad capacitor is connected to a 110 volt and 60 hertz alternating current supply. Determine the RMS value of the current in the circuit. First, let us here note down what are the given physical quantity, given value. You see, capacitor of the capacitor is 60 microfarad and 1 microfarad is 10 to the power minus 6 microfarad. So it is 60 into 10 to the power minus 6 farad, and the voltage of the source V is 110 volt. Frequency of the alternating source nu, it is 60 hertz. So angular velocity or angular frequency omega should be 2 pi nu. So 2 pi, pi should be substituted as 3.14, nu is 60, one can calculate omega. So now what is the capacitive reactance of the circuit? We know that capacitive reactance Xc equal to 1 by omega c. It is nothing but 1 by 2 pi nu c. Substitute nu 60 hertz, and now see 60 into 10 to the power minus 6. So finally you will get this value Xc in omega. We may finally calculate. So what is the root mean square value of current? Root mean square value of current I, according to Ohm's law, it is V by Xc. V is substituted as 220. The calculated value of Xc is substituted here. After simplifying this expression, it will turn out to be 2.49 ampere. So to say, the RMS current is calculated as 2.49 ampere. Now the second one, obtain the resonant frequency of a LCR circuit with inductance 2 Henry, capacitance 32 microfarad or 10 ohm. What is the Q value of the circuit? In your previous lecture, we have obtained what are LCR frequency, resonant frequency, and Q factor. You see, if the units are not coherent, it is not same. Here it is say microfarad. Here you have to calculate, see it as farad. So what are the given values here? The inductance AL equal to 2 Henry. Capacitance of the capacitor is 32 microfarad, means 32 into 10 to the power minus 6 farad, and resistance is 10 ohm. Now when we say at resonance, generally the frequency is given by omega equal to 1 division square root of LC. Resonant frequency omega, here it has been written as omega. Same thing, whether it is omega or omega R, does not matter. Now substitute for L, substitute for C, right? L 2, C 32 into 10 to the power minus 6. Whenever calculated, it will give you 125 radian per second. So that's the resonant frequency. What is the quality factor or Q value? It is given by 1 by R square root of LC. R is 10 ohm, L is 2 SI unit, C 32 into 10 to the power minus 6 SI unit. Just you calculate, it is 25. So Q factor or Q value is 25. Another problem in connection with this LCR circuit. A series LCR circuit with R equal to 20 ohm, L equal to 1.5 Henry, C equal to 35 microfarad is connected to a variable frequency 200 volt AC supply. when the frequency of the supply equals the natural frequency of the circuit, what is the average power transferred to the circuit in one complete cycle? Yes, see what is given here. What are the quantities given? That is important. In addition to that, here it is mentioned when the frequency of the supply equals the natural frequency, means it is the frequency at resonance. Resonance occurs. You have to calculate natural frequency. And at resonance, you know, inductive reactance equal to capacitive reactance and impedance is resistive in character. Okay, we will be also back to the discussion. Now here you see the supply frequency and natural frequency are equal at resonance condition of the circuit. Given resistance is 20 ohm, inductance is 1.5 Henry, capacitance is 35 microfarad, means 1 microfarad 10 to the power minus 6 farad. So it is 35 microfarad, means not 30, certain error is there here. It should be 35 into 10 to the power minus 6 farad. And the alternating current source here provides a voltage 200 volt connected to the parallel circuit, and impedance is given by the relation Z equal to square root of R square plus XL minus XC whole square. R, you know, is the resistance given to be 20 ohm, and at resonant condition inductive reactance XL equal to capacitive reactance XC. So put that value here, you will get Z equal to R equal to 20 ohm. So what is the current in the circuit? As per Ohm's law, current equal to potential difference by resistance, means opposition offered. And you know the net opposition offered by all the circuit element L, C, R. The three are inductor, capacitor, resistance. That is the net opposition Z. So I equal to V by Z. Z equal to R here. V 200, Z 20 SI unit. If you calculate, I equal to 10 ampere. So if current is 10 ampere, what is the average power that is being transferred to the circuit in one complete cycle? It is nothing but VI. Power equal to VI. I is calculated. V is given as 200. Substitute this value. Final value is 2000 watt. This is the final value. Average power is 2000 watt, and here current flowing through it is 10 ampere. Now the next example we will take off, that is related to a transformer. Here 1 kilowatt power is supplied in 200 ton primary of a transformer at 500 milliampere. The secondary gives 200 volt. Calculate the number of turns of secondary. Okay, so how to solve it? Given quantities are number of turns of primary NP equal to 200, that of the current flowing through the primary IP equal to 500 milliampere. It should be small m, capital A. It is error is there like this. This one is correct. So this is 500 into 10 to the power minus 3 ampere. Here you see again some mistake is being there here in the writing. It is not milliampere, it is ampere. The circuit one should be ampere and this one should be milliampere. ES is given to be 220 volt. EP is to be calculated. Potential developed EMF induced across the primary. And we know that input power is EP-IP. It is 1 kilowatt, means 1000 watt. Put IP here, 500 into minus 3. So EP into 500 into minus 3 equal to 1000. Solve this equation. It will give EP as 2000 volt. And now as per principle of transformer, ES by EP equal to NS by NP, the transformer ratio. Substitute for ES, that is given here, this one, EP which is calculated, NP that is given here, the 220 by 2000 equal to NS by 200. So after calculation, number of turn of secondary will be 22. So this is all about different problem. Many more problems are there. The more problem you work out, the more confidence you will get, which will be quite vital to get success in your different entrance exam. So practice as much problem as possible so that your fundamental will be more clear. I think you must have enjoyed this lecture by heart and soul. Thank you very much. Have a happy learning.